All right, so today we're going to continue on. We started yesterday with the notes on the periodic table. So yesterday we talked about the history and its brief development of the periodic table. Today we're going to talk about how it is arranged. So just remind you, this is what the periodic table looks like. You've got our metals, nonmetals, and metalloids. And then there's the wide version, which the way it should look. And this is the way that you'll see it in a lot of places. In fact, if you walk around the school, you'll actually see it painted on the wall this way. I used to have it that way on this wall, but I decided I wanted to have more space for other things on my wall, so I painted over it and did a more compact version because I didn't want to take up the whole wall anymore. Anyway, so today we're going to be moving on and talking about how it is organized, the things that you can see in the periodic table, and how to use the periodic table really to help you do chemistry. So modern periodic table consists of arrangement of boxes for each element that contain the element's name, chemical symbol, atomic number, and average atomic mass. Now, most all periodic tables will have all of this information. Some periodic tables have additional information that is not one of those things, but pretty much all periodic tables are going to have the name, symbol, atomic number, and atomic mass. And so some of them would show you state of matter, room temperature, oxidation states, type of element, and so on. So this is generally what your standard square on the periodic table looks like. You've got your element name, the atomic number, the symbol, and then the mass. Now, they're not always in this order or this configuration. So the name obviously is going to be the full name. The symbol is going to be its chemical symbol, which, as you should know by now, is either a capital letter or a capital letter with a lowercase letter. So no more than 2 letters. The atomic number is always going to be a whole number. The atomic mass, the average atomic mass, as we learned in the previous unit about the average weighted atomic mass, is always going to end up being a decimal number. You will notice on some periodic tables that you've got numbers in parentheses. Those are for the synthetic elements that we can't actually figure out their mass because we only know of one isotope, or they don't have any stable isotopes for us to figure out the average atomic mass. Because in order to figure out the average atomic mass, you have to have the percent abundance of the different isotopes. Well, if there's only one isotope, or if we can't figure out the masses of the isotopes, then that's why those have the mass in a parentheses, because they don't have any stable isotopes for us to figure out the atomic mass. We just use the mass of that isotope. All right. So columns, those are the vertical ones, up and down. Columns, just like the columns that hold up a building, are vertical. Columns on the periodic table are called groups or families, right? This is because members of a family tend to look alike and they tend to behave alike. Elements in the same column share common characteristics and very common properties. Remember, the periodic law and the law of octaves that John Newland's figured out, every 8 elements. Now, it's not really necessarily every 8 elements anymore, but we've figured out a reason for that 8, which we'll get to later. But the repetition of these patterns, if they make it to where they're all in the same column. So when the pattern starts to repeat, we go to the next column, and then so everything in the same column has similar properties, just like family members do. All right. You might recognize one of these people, and you might be thinking that the guy here in the middle is me, but it's not. This is me. Okay. This is my older brother. People think we're twins, and no, we're not twins, but he's actually older than me. But we do look very similar. You can tell when you see us together, it is obvious that we are brothers. We look a lot alike. We act a lot alike. We sound a lot alike. So we have very similar characteristics. And these 2 young ladies here are our cousins. Now, they are both very similar. Notice they have very similar chins, very similar nose and smiles. They act a lot alike. They're very similar. They don't look that much like us. We are related. They are our cousins, but they are sisters, and we are brothers. There are some characteristics in our family that is very, very dominant characteristics, as you can obviously see. But element families are the same way. Element families they are very, very similar. They behave the same way, they look the same way, and they act a lot alike. Okay, so that was fun. So these similar chemical properties are due to the arrangement of the electrons in the electron cloud of atoms. All right, so remember, the nucleus has the protons and the neutrons, and then the electrons are flying around it. But they're not just flying around it all random. There actually is an order to it. And actually the next unit that we're going to talk about is the configuration of the electrons. But how those electrons are arranged as they move around the electron cloud, that determines how the atom will actually behave. And that determines its chemical and physical properties to a large extent, because the outer electrons, those electrons in the outer cloud, those are the only ones that come in contact with other elements. So we talked about this briefly in a previous set of notes, but if I have an atom here with its electron cloud, another atom with its electron cloud, when they come together, it's the electron clouds that meet. So it's how those electrons interact with each other is what determines most of the chemistry that we're going to learn about. So we're going to discuss electron configuration in Unit 4, the next unit. But for now, what you need to know about electrons in the nucleus is that they orbit the nucleus with different levels of energies. Now, this was something that was proposed by Niels Bohr. We talked about that in the atomic theory notes. Niels Bohr proposed that atoms would be, or electrons are surrounding it in defined orbits. He called them energy levels, right? Electrons in the outermost energy level, the electrons on the very outside of that electron cloud, are called valence electrons, right? And it's the valence electrons, the ones on the outside, valence. The valence electrons are the ones that determine the chemical properties of the elements. They're the ones that determine the chemistry. They're the ones that are doing everything that they're doing. And honestly, if you learn how electrons behave, and if you learn how the valence electrons interact with other valence electrons and why they do what they do, chemistry becomes a whole lot easier. So pay attention to this, all right? Elements in the same group or family have the same number of valence electrons, because again, we just said valence electrons are what determine the chemical properties. So if they have the same chemical properties, they're going to have the same number of valence electrons. Now, the differences between one atom and one element here and another element has to do with how far those valence electrons are from the nucleus. So as you get bigger atoms, the bigger atoms are going to have valence electrons farther away from the nucleus. And so that's going to change a little bit about the properties, but how they behave and what their chemical properties are dependent upon the physical or the arrangement of those electrons. The valence electrons on the outside, how many they have. So if you look at it, I'm going to show you just these main group elements. Now, what you see here, groups 1, 2, 13, 14, 15, 16, 17, and 18, these groups are called the representative elements, because in this set of the periodic table, you take out those middle section and you have just the outer edges of the periodic table there, the big section here and the little small section there. You take those out, just these two sections, and you have pretty much all chemical and physical properties represented. Like if you want to say, well, I need an element that does this, there's probably one in this group that does that. I want an element that does this. There's probably one in this. So they represent everything, just like the House of Representatives in the Congress theoretically represents the people. All right, so there's somebody there that represents my views. There's somebody there that represents your views. There's somebody there that is representing your interests. That's why we call these the representative elements. Okay, so but you'll notice group 1, this dot right here, represents its valence electron. So everything in group 1 has 1 valence electron. Everything in group 2 has 2 valence electrons. Notice the 2 dots. Everything in group 13. Now I want you to notice, if you take out the 1, it's a 3. All right, 3 valence electrons, 4 valence electrons, 5 valence electrons, 6 valence electrons, 7 valence electrons, 8 valence electrons, with the exception of helium. All of these have 8 valence electrons. The reason helium only has 2 is because helium only has 2 electrons. It can't have 8 valence electrons when it only has 2 electrons total. Why is helium not over here? We'll get to that later. But helium is here for a reason. Even though it only has 2 valence electrons, it is the exception. Everything else has the same valence electrons. So if I ask you, how many valence electrons does an element have? All you have to do is simply look at the column number, and that tells you the valence electrons. 1, 2, 3, 4, 5, 6, 7, 8. Now, when you see the column numbers, again, it's 1, 2, 3, 4, 5, 6, 7, 8. And actually, these 3 columns all have 8 valence electrons. At least for the purposes of our class, that's what we're gonna say. It's not actually the case, but we're gonna say that for this class. So all of these have 8, and then when you get to ones that have a greater than 10, just look at the ones place. So 1, 2, 3, 4, 5, 6, 7, 8. So you'll notice as you go across the periodic table, it's 1 to 8, and then 1 to 8. And that's how you tell how many valence electrons it has, and that determines its properties. Right? Those valence electrons are also used to separate the periodic table into blocks of elements. And as you look at the periodic table, you can see that there's kind of a big section over here, and then there's a small little rectangle right here, and there's a big wide rectangle right here, and then these section down here. So you've got these 4 sections of the periodic table that are kind of blocked together, and that has to do with its valence electrons also. All right. These sections and these blocks are going to be defined more in Unit 4 when we talk about electron configuration. But for now, you just need to know what they are and what they're called. We'll discuss why later. So you have the S block, all right, consists of groups 1 and 2 and helium, even though helium is over here with the last column, it's part of the S block. So it's kind of weird. Then you have the D block. It consists of groups 3 through 12. These guys right there, okay, groups 3 through 12 are the D block. So the S block and the D block. Groups 13 through 18, the large section here, right, 13 through 18 are called the P block. And then the ones down at the bottom are the F block. They're traditionally placed at the bottom of the table, but as we discussed before, they actually belong up inside the table. So that's that. So again, we have our S block, and helium belongs over here, right? We have our D block, and the D block is groups 3 through 12. The P block, so the P block includes all the nonmetals and metalloids. All right, and then the F block are these guys down here. So S, P, D, and F are the blocks of the periodic table. S, P, D, and F. Now, I've heard lots of stories or reasons. I've never actually bothered to look up why they're called S, P, D, and F. I'm not really sure why it has that, but I heard once that had to do with the names of some famous scientists that had a lot to do with nuclear physics and stuff. So we had Schrodinger, Pauli, Dirac, and Fermi are some very famous guys that had a lot to do with the development of atomic theory, modern atomic theory. So, all right, so let's talk about some definitions here. We talked about the groups. The columns are the groups or families. Rows are the horizontal ones. Rows are called periods, all right? So you have one period, and then you go to the next row, and that's a new period, but that period has the same properties. So if you go across the periodic table, then when you get across the periodic table, you've done all the properties. You go down to the next row, and those properties repeat themselves. That's the periodicity of the periodic table. As you move from row to row, the properties repeat themselves, right? Because a period is something that repeats at a regular interval. So that's why we call them rows. Each row contains the same pattern of chemical characteristics and then repeats. So we call them periods. I just said that multiple times. Hopefully it sticks into your head. All right. Each period also represents an addition of an energy level in the electron cloud. So remember, Bohr said that the electrons orbit the nucleus in energy levels. So the first row has one energy level. The second period has 2 energy levels. The third period has 3 energy levels. So every time you go down a row, you're adding a layer to the electron cloud, adding an energy level. We'll get into that more when we talk about electron configuration in a couple weeks. All right, as I already said this, I already mentioned this to you, elements in groups 1, 2, 13, and 18 possess a wide variety of chemical and physical properties and are therefore called representative elements because they represent the majority of the possible chemical properties. So that's why they're called representative. So if I tell you to just look at the representative elements, then I want you to ignore the ones in the middle. All right, the representative elements are those found in the S and the P block. All right, we're going to use representative elements more than any of the others because, well, they represent all of the physical property or chemical properties. So those are your representative elements in groups 3 through 12, otherwise known as the D block, represent a gradual transition in properties from metal to non-metal. So you have over here in groups 1 and 2, they're very metallic. And as you move across the periodic table, they become less metallic in their character and they become closer to non-metals. So we call them transitions. They transition into the non-metal block. So the F block of elements normally fits inside of the D block, as I showed you the wide version of the periodic table where the F block is up inside the D block. Therefore, they are called the inner transition elements. So you have the transition elements, and then you have the inner transition elements. They're all transition elements. Just the inner transition elements are the ones on the inside. So metals are on the left of the periodic table, with the exception of hydrogen. And you'll notice, again, most all elements, if you just randomly grab an element, you have a pretty good chance of grabbing a metal. All right, the metals are on the left, non-metals are on the right. So that's important. I will ask you, where are the metals located? Where are the non-metals located? On the left or on the right? Specifically, we would say the left of the stair-step line and to the right of the stair-step line. And metalloids are then on the stair-step line. They're touching that lovely red line there. That is going to be the end of it for our notes today. And now you're going to have a worksheet that is going to go over the stuff from yesterday and today, putting it all together. So good luck and have fun with that.